Okay, what I'd like to do is introduce really one of the most important skills that you guys are going to develop in the entirety of physics. So the skill that we're developing today, that we're starting today, starts with a free body diagram, and then it continues with a kind of mathematical model that you build that comes from the free body diagram. But if you don't draw the free body diagram correctly, then you can't build the model to describe the forces algebraically. So it's kind of a two-step process. So I'm going to first draw a sketch. A sketch is not a free body diagram. A sketch is like a picture that kind of shows you what's happening. A free body diagram is very different. So one of the sketches that you guys had was of a lamp, and it was just resting on a table. So let's say that there's a lamp here, and it's sitting and it's not accelerating on a table. So the free body diagram portion is really the first thing that you do when you're doing a dynamics problem. So the free body diagram is simply just a box that illustrates the forces acting on this object. What's one of the forces acting on the lamp? Gravity. Okay, so I'm going to draw a gravitational force. Now the size of the vector ray that I draw indicates the magnitude of the gravitational force. So I'm kind of making a quick graphical representation of the size of these forces. Are there any other forces acting on the lamp? Okay, there's a normal force. Drew, what's the direction of the normal force? How does the size or the magnitude of the normal force compare to the magnitude of the weight force? Ashley, what do you think? What would happen if I made a normal force, or an F sub n, that was illustrated like this? Is that correct or incorrect? Incorrect, and why? Okay, it needs to be equal. Why does it need to be equal? Why does the normal force have to be the same size as the weight force? They cancel each other out. So let me ask you this question, Shantae. Is the sum of the forces acting on the lamp in the y direction equal to 0? Yes. What's your evidence for that, Susie? I agree that the answer to this question is yes. But why is it heck yes? What's your evidence? How do we know that the sum of the forces acting on the lamp needs to be 0? Say that one more time. Okay, but I'm asking for a physical, because the lamp isn't moving, and you guys need to invoke the laws of motion when you answer these questions. Is the lamp not moving? Newton's work in the 17th century told us that if an object was at rest, and it stayed at rest, then the condition was that the net sum of the forces acting on the lamp externally must be 0. So we have evidence that the sum of these forces is equal to 0. The second step that we take, notice that this is an intermediate step, asking that question if the sum of the forces is equal to 0. The second step that we take is to write a dynamics equation. So I'm just going to simply look at the forces here and add them all up together. So is the normal force a positive or a negative force based on our convention for vector direction in the y-axis? Annie, what do you think? Positive. So I'm going to simply write the normal force. I don't need to write a positive in front of it because we know that it's positive if there's nothing there. And I'm going to add to it any other forces acting on the lamp. Well, we know that we have to add to it the gravitational force. Is that positive or negative? It's negative. So I can either make that a negative sign, or I can say that the gravitational force is in the negative direction, and I'm going to set them equal to 0. I can set them equal to 0 because we've answered this question. The sum of the forces going up and down has to be 0. The system's at rest. My dynamics equation now looks like this. So we've done like the easiest dynamics equation possible, which is just a lamp sitting on a desk. But the point is, what we've captured here, drawing the free body diagram, asking ourselves, what is the vector sum of the forces? And it's a binary question. It's either yes or no. The sum of the forces is either 0 or it's not 0. What's another condition other than a lamp at rest where the sum of the forces would be equal to 0? There's one more physical condition that could meet this criteria. Any ideas on that? What if I said, let's change this scenario. Let's do another problem. And I think it'll be able to answer that question. Let's take the same lamp, and we're over at Annie's house, and the McLeod family always does this kind of weird stuff where they like tie a rope around the lamp and they pull it across the table. It's a weird physics family. So we're going to assume that there's a rope pulling the lamp to the right, and we're given some additional information that the lamp is moving at a constant velocity, meaning that the lamp slides across the table and its change in position with respect to time every second remains fixed. I would like you guys to draw a free body diagram. So step number 1 is to draw a free body diagram of the different forces acting on that lamp. Okay, let's check in with Emma. Emma, what's one force acting on the lamp sliding across the table at the McLeod house? Friction. Okay, you started with the toughest one. What is the direction of the frictional force? Excellent. Opposite the direction that it's going. We'll get back to this in a bit. I'm going to call this F sub FR. Sometimes you'll see a frictional force abbreviated with a cursive F, but either of those that's just semantics, however you want to mark frictional force. It's definitely, you guys need to know that friction always acts in a direction opposite motion or intended motion. So it doesn't have to be moving. If I try to put a force on this bottle and I put a small force and it doesn't move, well then there must be a frictional force opposing the motion because I applied a force with my finger and it didn't move. So the frictional force opposed my applied force and canceled it. They canceled and it didn't move. So I can have frictional forces on things that aren't moving. This lamp in this particular sketch is moving and the frictional force is in fact to the left. Let's check in with you, Morgan. What's another force acting on the lamp? Okay, and forces in ropes or strings are known as, anyone? Good, tension. I can call it F sub T. Sometimes you'll see it just as a capital T. Tension in a cable, a chain, rope, strings. We just call that tension. Other forces acting on this. Let's check in with you, Chad. What's another force acting on the lamp? Gravity. And by the way, any free body diagram that you draw that exists on any planet, but most of them will be on planet Earth, of course, include gravitational forces. Any other forces? Anything I've left out? Milop? Good. Normal force. The normal force is still there. I'm just drawing it as a dashed line because I've run out of different colors. And so now we can see that we have 4 different forces. Let's start in the y direction with our intermediate question. Is the sum of the forces in the y direction equal to 0? Ken, what's our answer to this? Yes. What's your evidence for that, Ken? It's not moving up or down. So I can, when I add up all the forces in the y direction, they're going to be equal to 0. Bella, I'd like you to answer the second question, which is the sum of the forces in the x direction equal to 0? No. Agree or disagree? Richard? Okay, this is the most commonly mistaken part of early dynamics. You guys just fell into Aristotle's fallacy right here, which means that you have the same gut level feeling that the great Greek philosopher had. So don't feel badly about being wrong. But why are they wrong? Garrett, articulate why the answer to this question is not no, but in fact the answer is yes. If the acceleration is 0, the net force must be equal to 0. And that's hard to wrap your head around, which is why I'm trying to say it with so much emphasis. Something that is moving at a constant velocity has no leftover force. And when I wrote Newton's first law on the board, I acknowledged, hey, kids will never argue with me on the idea that if it's at rest, the sum of the forces is equal to 0. But they are innately uncomfortable with the idea that the vector sum of the forces is still 0 when it's moving, as long as it's not accelerated. So therefore, when I add up all the forces in the x direction, the vector sum of them is still going to be 0. Okay, I'd like you to write out your dynamics equations. I'm going to give you guys a couple of seconds to write them out now that we've correctly drawn our free body diagram. Okay, let's check in with this problem. We've got a lamp being moved across the table. What's special about the way that it's being moved across the table? Okay, it's being pulled at an angle, so that's something different that you guys have seen. What can I say about the nature of its motion? Is it accelerated or not accelerated? It's accelerated. This information in blue simply gave you the acceleration in coded form. We know what the acceleration is. This is a kinematics problem. So I can simply say that VF is equal to VO plus AT and solve for my acceleration. It's going to be VF minus VO over time, and therefore I'm going to get 3 over 3, or my acceleration is 1 meter per second squared. So I do have acceleration. Is the sum of the forces in the y direction equal to 0? Yes, it is. It's not moving in the y direction. It's accelerating and moving in the x direction, but it's not even moving in the y direction. Its velocity is 0. We have another example of the independence of vector components. And so therefore, I can say that the sum of the forces in the y direction is equal to 0. Sum of the forces in the x direction, not equal to 0. This is the first practice problem that we've done where we're going to have some leftover force. I've drawn the tension force up and to the right at 30 degrees because that's the direction the string is being pulled with. I'm going to resolve that tension force into its x and y components. I have an x component of tension and I have a y component of tension. What other forces do I have acting on the system? Friction. Annie, which way does friction act? To the left, so I have a frictional force. Any other forces acting? Garrett? Normal force. The normal force is still here, but recognize now that the normal force is probably going to be, well, it's not probably, it's going to be smaller because I have 2 forces going up and only 1 force going down. We should be able to recognize that if the sum of the forces in the y direction, then this plus this is going to be equal to that. So that's probably even smaller than the way that I drew it. So we've answered our first primary question, which is the sum of the forces in the y direction is equal to 0. We know that because it's at rest. Write my dynamics equation for me. Jenny, what would be a dynamics equation for the y direction? Okay, negative Fg plus Fn, excellent, is equal to 0. If you've drawn your free, this is probably the most important thing that one of the top 5 most important things I'll say throughout the course. If you have drawn your free body diagram correctly, you should be able to walk up to the free body diagram with blinders on and simply write down the forces. That's it. Fn and Fty are up, the force of gravity is down, and write an appropriate dynamics equation with your directions there. Harry. Okay, so what I'm saying is that anytime you get a force acting on an object that's not straight up and down or left and right, you have to resolve it into its x and y components. Just like in the projectile problems that we did in a previous unit, if there was a football being kicked at some velocity, the first thing that you would do is separate it into how much of that velocity is going to the right and how much of that velocity is going up. And what I'm telling you is that nothing has changed when we deal with forces. This tension force is useless to us. And now that I've represented the force in component form, I don't need to think about it going up and to the right. I've already dealt with the amount going to the right, and I've already dealt with the amount going up. So I can stop there. Does that answer your question? Okay, let's move on. We said that the sum of the forces in the in the x direction is not equal to 0. Help me write a dynamics equation for the x direction. TJ, help me write this out. And you should just be able to, you should be able to just look at the sketch and write down what you're seeing here. Well, it's not equal to the acceleration. It's equal to our net force, which eventually we will substitute as mass times acceleration. Newton's second law is F equals ma. And so in this particular problem, we're going to eventually need to know the mass, which I didn't write down here, but I'm going to have to give you. But we do know the acceleration in the problem. If we knew the mass, and we know the frictional force, we should be able to figure out the tension. So that was my mistake. Let me add the mass in this problem. Let's call it 2 kilograms. So if the mass is 2 kilograms, I can solve this expression for Ft. Ftx is going to break down into what? Ft times, what am I going to multiply by Ft? What am I going to multiply by Ft, Mila? Excellent. Cosine of the 30-degree angle. So it's going to be tension times the cosine of theta, which gives me just the x piece. And I'm going to subtract the frictional force, and that's equal to mass times acceleration. I can now solve this expression for Ft. Ft becomes ma plus the force of friction divided by the cosine of theta. I know I'm about to get more excited about this than you, but here's what's beautiful about what we just did. You guys just crafted from scratch, using 2 simple ideas, you crafted an equation for a tension force when you're dragging a lamp across a table at an angle and it's accelerated. There's no point in memorizing this because anytime we change the situation, the entire equation would change. So what you're being trained how to do in Unit 2 is to build your own algebraic model to describe a specific scenario. And all of the scenarios can have differences from each other. So don't look at this and say, oh yeah, that's the tension equation. You just made a brand new tension equation that deals with that particular situation. I think it's really cool. And so hopefully you can get to this point, and then now we're just ready to substitute some numbers in. Our mass, which I added late into the game, is 2 kilograms. The acceleration you guys calculated, given the initial kinematics equation, was 1 meter per second per second. The frictional force was 25 newtons. And I have to divide all of that by the cosine of 30 degrees. I'll give you guys a minute to process that, and then we'll move on. Okay, you should have arrived at dynamics equations that look like this. That's my weird dashed line to match the pattern for the normal force. The normal force is positive. It's going up. I have to subtract from it the weight. It looks an awful lot like it did when the lamp wasn't moving. And the fact that it's sliding across the table at a constant velocity does not affect the fact that it's at rest in the y dimension. So it's not even moving, even though it's moving. It sounds weird to say that. And in the x direction, the sum of the forces is equal to 0 because it's specifically not accelerated, so therefore I get a tension force minus the frictional force is equal to 0. Any questions here? Emma?
Would the friction and the tension one be the same if, I'm trying to figure out how to say this. So like, if it wasn't moving because of the friction and the force, like it'd still be the same.
Yeah, that's right. So we're gonna find out with a little bit more deeper study that the frictional force is a variable sized force up to a certain amount. It can have a maximum value. So if I pull on it with a little bit of force and it doesn't move, the frictional force would have to be the same size. Because if the frictional force were bigger, then it would accelerate that way, which is not happening. But the frictional force gets larger and larger and larger, but it has this maximum value. So once I exceed that maximum value, I could then start to accelerate that. So once the tension force got bigger than the frictional force's maximum value, we could accelerate the system to the right.